In this lecture, we will introduce a simple data structure called heap. Heap has two properties, the shape property and the heap property, to be satisfied. Then, after showing these properties, we will talk about what kinds of operations that it supports and analyze the corresponding time complexity. Using a heap, we can sort numbers. And then this is called a heap sort algorithm. Finally, we will show that a heap can be stored in an array so that it is a very easily implementable data structure. So what is a heap? A heap, or we can call it a binary heap, is a binary tree, and it satisfies two properties, the shape property and the heap property. For the shape property, it says that the binary tree will be having the shape such that all the levels except the deepest one, they are fully filled. We will see the examples soon. And then also, the deepest level is filled from left to right. So this is called the shape property. And then numbers can be stored inside the node of the heap. And then for the numbers to be stored, they need to satisfy the so-called heap property. So for a particular node, the number that is stored inside must have value smaller than or equal to the number stored in any of its children. So let's see the examples. So first of all, the shape property. So this is a binary tree that has 1, 2, 3, 4, 5, 6, 7, 8, 9 nodes. Okay. As we can see, for this tree, all the levels are fully filled except the deepest one. And also for the deepest one, the nodes are filled from left to right. This is a binary tree that satisfies the shape property. On the right hand side, we see a different binary tree. This time it has one more node, and we can see that although that for the first three levels they are fully filled, but the deepest level here, we will see that the nodes are not filled from left to right. So we have a node here, a node here, but then there should be, if there is another node that is going to appear, it should be the children of this node instead. So in this case, this tree, this binary tree, does not satisfy the shape property. And then we can also observe that all the heaps, if they have the same number of nodes, they must have the same shape. Now, how about the heap property? So here we have an example such that inside the nodes there are values stored. So on the left hand side, if you check every node here, for instance, we check this node, the value inside the node is smaller than or equal to the values inside any of its children. So we see that on the left hand side, the numbers are filled so that they satisfy the heap property. On the right hand side, we have also numbers filled, but we will see that for some particular cases, like this node and this node, this pair of nodes, the node in the above and the node of its child, the numbers are not in the correct relationship. This is having a larger value, this is having a smaller value. The violation also occurs here. So we see that as long as there is some violation, the heap property is not satisfied. Now, because every node will have values smaller than or equal to the children, we can easily show that the root will be the node that is always storing the minimum value. So we are actually going to use a heap to maintain. So this is the data structure problem. We are going to use a heap to store a set of numbers. And then we will talk about what kinds of operations that it supports. But one most important operation is we want to make use of a heap to find the minimum item, the minimum number of a set of numbers. Okay, but before we define the operations that a heap supports, let's check the height of a heap. So let's say h is equal to the height of a heap with n nodes. Now when we talk about the height of a tree or height of a heap, there are two different ways that we can talk about it. We can count the number of edges on the longest path from root to leaf. So here the height is 1, 2, 3, 3 edges. But instead of talking about the edges, we can also talk about the number of nodes appearing in the longest root to leaf path. So in this case, the height is, we can talk about it, it has 1, 2, 3, 4 nodes. And here we let h to be the node height, so we focus on the number of nodes instead of the number of edges of a heap. Now we see that n has to be greater than 2 to the power h minus 1 and then minus 1. Now, what is the meaning of this number? This number is actually the total number of nodes in the top h minus 1 levels. So the root node, the first level, and then the children of the root, the second level, and so on and so forth. So they add up to this number. And then n has to be smaller than or equal to 2 to the power h minus 1. And what is 2 to the power h minus 1? So 2 to the power h minus 1 is the number of nodes for a fully filled height h heap. So this is the maximum number of nodes. This is not log, this is in h levels. Okay. Now because of this, we take log on both sides, we will see that roughly h minus 1 is less than log of n, is less than or equal to h. So in that case, we see that h is of theta of log n. Now, what does a heap support? So a heap is used to maintain a dynamic set of numbers. Here, dynamic means that the set S here, we will change it from time to time. Sometimes we may have numbers added to the set S. Sometimes we may have numbers deleted from the set S. So we call it a dynamic set. And then this dynamic set will have three operations. The first one is we want from time to time find out what is the current minimum of this set S. Because S is going to change from time to time, the minimum may change. And the second one is the insert operation. This supports adding a new number to S. So in this case, S will be changed. And then the third operation that we want to support is extract min. And for extract min, we are going to remove the minimum item of S. So this also changes the content of S. And then we will see that when we remove items, it must always be the minimum. So insert, you can insert anything, but extract, you can only extract min. And heap is a data structure that can support all these three operations quickly. We will show that find min is done in order 1 time. Insert and extract min can both be done in order of log n time, where n is the number of items in S. So find min takes order 1 time. It is because we have already mentioned that the minimum item is always stored at the root. So if we access the root, we look at the content, then this is the minimum value. Now insert. Now to support insert, we are going to make changes to the structure of the heap. And in this way, so this is the idea of how we are going to do. So first of all, when we perform insert, we will first change the heap so that the shape becomes correct. So because we are now having one more item, we need to change the shape so that we can accommodate the new item. and we change the shape, and then we will add a new node correspondingly. After that, we will simply put the new item to the new node. But in this way, we only have the shape property okay, but the heap property may not be correct. So in the third part, we are going to fix the heap property. So we will see an example soon about exactly how we do each of these steps. So let's say on the left hand side here is the original heap before we perform the insertion. And now we want to insert the number 5 here. So what do we do? So this is the heap that is storing how many numbers? 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 numbers. We will now add one more node to get to some binary tree for storing 10 numbers. And this binary tree satisfies the so-called shape property. So in that case, the new node must be added here. And then we put the newly inserted number, this number 5, to the new node. So this is now fixing the shape property while putting the new value into the new node. But at this moment, the heap property may not work. So for instance, if we look at these two nodes, the parent has a larger value, which is not okay. So what we are going to do? So let's highlight the node that is currently storing the inserted value. So this is the number 5 here. We will see that this 5 and this 23 are not in the correct order. So in that case, we are going to swap them so that we exchange the content inside. After this, we will now have 5 here and 23 here. So we will also see that this now 5, which is the highlighted node, is now moved up one level. What we are going to do next here is we will further compare this highlighted node with the parent. And the parent is still larger. So in that case, they are not in the correct order. So we will perform another swapping. So in that case, we will swap 5 and 8 so that we get this case. After the swapping, we will find out that 5, the highlighted node, is now okay, have the correct heap property with the parent node. So in that case, the operation will end. So we will just basically move the newly inserted node here, the highlighted node here, up to a location such that everything works. And then the correctness why this is working, we just need to focus on the movement of this highlighted node. It is because we can show that only the highlighted node and its parent at any time may violate the heap property. If you look at this case, this is the highlighted node and this is the parent. This is before we do anything. So that all the parent-child relationship, they satisfy the heap property here. All these edges are okay. This is the only possible edge that is not okay. Now after swapping, this edge now becomes okay. All these edges are previous edge. So they are followed from the previous heap that they are okay. And this is the only edge that is not okay. So we are going to check it. And finally, after moving this, we will see that this edge now becomes okay. All the remaining edges, they are all okay. But then this edge could potentially be wrong. This is the only possible edge that is wrong. But if this edge is also okay, that is when this node has a larger value, and then we don't need to do the swapping anymore, then the overall heap will be now okay. So this is somehow explaining why this insertion operation is correct. Now as for the time analysis, we will see that whenever there is a swapping, the highlighted node will move up one level after each swap. But the tree has only log n as its height, so there are at most order log n swaps performed. And for each swapping actually just exchange the content of the nodes here. So the time to perform this operation is independent of the total number of nodes here. We just look at these two nodes and they exchange the value. So that's why each swap, we say that they can be done in constant time, order 1 time, independent of n. So there are order log n swaps, each one takes order 1 time, so insertion takes order log n time. Now here, the n is denoting the size of the heap, the number of nodes stored in the heap. So this is insert. Now how about extract mean? Now for extract mean, the idea is also similar. So basically, we are going to fix the shape property and then fix the heap property. So the description, how do we fix the shape property? So first of all, we are going to copy the content of the last node and then copy all the information of the last node to the root node. Remember, we are doing extract mean. So the original content of the root node will no longer be needed because it is storing the minimum. So we are going to copy the content of the last node to the root. And now we are going to change the heap structure. So we make it into the correct shape by removing the last node. After that, the shape is now okay, but then the heap property may not be satisfied. So we are going to fix the heap property. Let's see an example run. So let's say this is the original heap, and then we want to perform extract mean. So in the end, this 3 should now be gone. So this 3 is gone, so what should we do? So we first copy the content of the last node. This is the last node, because we are feeling this is going to be the last one. Copy the content of the last node to the root. So 38 is now moved to the root, 3 is gone. And at the same time, we also remove the last node. So now you see that this is corresponding to a binary tree that has the correct shape property. But it is not yet a heap. It is because there could be violation of the heap property. Especially if you look at this 38 is now larger than this child and also larger than this child. So it's not working. So after that, we are going to fix the heap property. So how do we fix? So this is the key point. If there is a violation, so we are going to highlight the node that is storing the previous content of the last node. So we are going to highlight this node, focus on this node only. So we are going to check whether this node has a value larger than any of its children. If it is the case, so there is some violation, then we are going to swap this with the smaller of these two children. So 4 and 8 are both smaller than 38, but 4 is smaller than 8. So we are going to choose 4 to swap with this highlighted node. After swapping, we get 38 here. And again here, these two numbers, these two children, they are smaller, both smaller than this highlighted node. So we choose the smaller of them and swap. After swapping this, then we see that 38, it doesn't have any children anymore. So we will stop. Or actually, we will stop whenever we see that there is no violation. And here, there is no violation at all because there is no children. So we stop. Now notice that this is actually a bit similar to the insert operation in the sense that the highlighted node will always move down one level after each swap. And also, the operation of this extract mean, we just focus on the highlighted node without caring about the other parts of the tree. The reason is that we can show that at any time, only the highlighted node and its children, so this edge and this edge, may cause the problem. may be violating the heap property. All the other cases, like this edge, this edge, this edge, this edge, this edge, they are previously in the previous heap. So they are all okay in the heap property. And after swapping, so this is a case that is done. After swapping, we will see that all these other edges here, like this one, they do not change. The content doesn't change. So if they are okay previously, they are okay. And we are swapping the smaller of these children with the highlighted node. So this edge is also okay. What does that mean? It means that the only problematic case is the highlighted node with the new children that it has. So in that case, we maintain this invariant, we maintain this property that only the highlighted node may violate the heap property. This allows us to just focus on the highlighted node and then move it around. So this is how extract min is done. And then for the analysis of its time, it is also similar to that of the insert operation, because we see that if swapping is performed, the highlighted node must move down, and then it can move down only log n times. So altogether there are order log n swaps. Each swap can be done in constant time, so extract min takes order log n time.